Well, look, today I'm going to talk about physical layer security and wireless networks. And so obviously, I think it goes without saying that, security is one of the most important aspects of network design. Every day we hear about issues of security breaches and so forth. And as more and more, we rely more and more on wireless networks. I mean, security in wireless just gets to be more and more important. Now, of course, our cellular networks are pretty secure. I mean, I think certainly the wireless interface between cell phone and the base station is pretty secure. But there are a lot of emerging kind of wireless networks, particularly Internet of Things networks, where we don't have the same luxuries we have in terms of computing power and so forth, and tight infrastructure that we have with, say, a cellular phone network. So one of the things what I'm going to talk about today is physical layer security, which can serve as either a baseline security or complementary security to other methods for situations where we may not have the kind of resources that we need to provide the kind of security that we have today. And I'll motivate this a little bit more as I go through. But I would like to say that I'm particularly going to talk about an information theoretic perspective on this problem. There are a lot of other things involving that. I'll mention some of them at the beginning, but I want to focus, since I'm mainly an information theorist, I'm going to focus in on that aspect of it. But you should know that it's a much bigger field than what I'm going to talk about today. I want to thank a couple of colleagues, mainly Ursi Chorty, who's at INSEA in France, a couple of her former students, Madi Herfa and Miroslav Mitev. And together, Ursi, Madi, and I wrote a chapter in a book that's about to come out on physical layer security. And a lot of the things that I'm going to talk about today are in that chapter. And they helped me also put together some of these slides. So I wanted to call them out at the beginning. Okay, so first of all, today, how do we handle security in wireless networks? Well, mainly security is at the higher layers. We have, either primarily at the application layer, but also at the transport layer. We provide security primitives. And it works well, as I said. So why do we need to worry about securing the physical layer? Well, a couple of things. First of all, some of the good things about standard security primitives, and particularly cryptographic systems, is that they're immune to known attacks. There aren't any known physical attacks. They're out there, widely employed and tested, and they allow us to do trustworthy authentication. Some disadvantages are, first of all, they're built on unproven assumptions. That is, we think they're secure because we can't break them, but there's no proof that they're secure. Typically, we assume that there's already a physical layer connection has already been established, and they're computationally intensive. So this is a problem, for example, Internet of Things, where the terminals may be low complexity. And they also require significant infrastructure. Again, a potential problem in Internet of Things where the infrastructure may be quite light. So what about physical layer security? Well, the thing about physical layer security is based on information theoretic principles. It's secure, it's quantum secure. There's also quantum information theoretic security. It's fast and lightweight. That is, it's the same kind of complexity as error control coding, which is commonplace. And you can actually, if you want to use encipherment, you can actually generate key or distill key from on the fly in the physical layer. Now, some disadvantages are oftentimes there are assumptions on eavesdroppers' channels, which are unrealistic or go beyond what we can expect in practice. Much of the work is on asymptotic. is asymptotic theory, based on asymptotic theory, just like other parts of information theory. I'm going to talk about that a bit more later. And it's still in its infancy. It's not tried and true like the kind of security that we deal with today. So I'm going to talk about that today. But what can go wrong with the kind of security we have today? Well, as I mentioned, a prime example of where today's security might break down is in the Internet of Things, where we have massive numbers of terminals. They may be very low complexity and low cost. You know, we're talking about $10 sensor versus $1,000 smartphone. And the numbers are such that traditional handshaking and key distribution and so forth, these kinds of issues, key management, much more difficult to deal with. And the infrastructure is quite light. They might be cell-free and so forth. So there's a lot of architectural issues and practical issues in Internet of Things type applications that mitigate against using traditional methods of securing wireless links. And of course, it's a big concern. There's been a lot of press about Internet of Things and privacy and security concerns. One example, which I was involved with some research, this is Sajal mentioned the energy systems. This is an energy system example of what can go wrong with IoT networks when you don't have them secured. And it involves something called a MAD attack, or manipulation of demand attack, where you have a botnet controlling a lot of IoT devices like Nest devices on your air conditioner or refrigerator. And if you can get a botnet out there of the Mirai size botnet, like 600,000 bots, and controlling that many loads, then you can control a load instantaneously that can change the demand by 3 gigawatts, similar to having access to the largest currently deployed nuclear plant. So you can basically bring down the grid if you're able to get in there and control that many IoT devices. Now, there aren't really enough out there today to make this happen, but someday there will be, and so this is a potential issue. So IoT covers a lot of things: factory automation, self-driving cars, and so forth. A lot of very important and mission-critical things involve Internet of Things, including power grid. So it's important to think forward about ways that we might be able to secure the IoT, for example, given the limitations that we have on the devices and the network. So what can physical layer security offer? Well, there's physical layer security issues in almost all parts of security. Node authentication, there's a lot of work on using biometrics or physically unclonable functions to identify wireless hardware, or message integrity, also the same thing, trying to ID hardware by looking at message physical aspects that in the message that are unique to given devices. There's also message confidentiality, that is the thing that would be handled by encipherment, say, in a traditional system. And that's what I'm going to talk about today. So I'm going to talk mainly about message confidentiality based on so-called wiretap channel model, but it can also be used for secret key generation, which I'll talk about also in a minute. So here's an overview of my talk. So as I said at the beginning, I'm going to focus in on the role of information theory in this area. And I'll focus mainly on two things: message confidentiality and data transmission, and privacy in sensing systems. And again, I'll take an information theoretic approach in both cases. Excuse me. So I want to also, at the very end, when I was putting this talk together, I was planning to spend more time on this, but when I went over the talk, I realized I'm not going to have time. So I'm just going to talk very briefly about a couple of other issues, some of which actually go back maybe a decade or so, where information theoretic analysis can also help looking at security issues, other security issues besides message confidentiality. All right, so let me now talk about message confidentiality in transmission systems. And again, the idea is that we want to rethink security design. And conventionally, of course, as I said at the beginning, security in wireless networks or in networks in general is a higher layer issue based on encryption, key management, and so forth. Now, again, if you have a massive number of devices, low cost, low latency, with little or no infrastructure, this approach breaks down. So physical layer security is a way to get to security by exploiting imperfections in physical channels like noise, fading, and so forth in order to provide a layer of security. And in the end, you can just think about, just like we think about joint source and channel coding, you can think about physical layer security as sort of joint reliability and security coding. So reliability is channel coding, security is, well, encoding for physical layer security. So that's the way to think about this. We're just moving the security into the physical layer, just like we do the reliability of data transmission. So what is the basis for information theoretic security? Well, it goes back, just like almost everything in information theory, it goes back to Claude Shannon. And he had, of course, he had a famous 1948 paper where he laid out the principles of information theory, but he had a 1949 paper where he looked at the security of cipher systems. And so he looked at a system like the one I've shown on the screen here. You've got a message, you have a transmitter we call Alice, a legitimate receiver we call Bob, and an eavesdropper who we call Eve. And Alice would like to send a message M to Bob reliably while keeping it secret from Eve. And so in Shannon's model, this is, like I said, this is a cipher model. And in Shannon's model, Alice and Bob share a secret key K. And so Shannon was interested in whether you could achieve perfect secrecy in a model like this. And I'll just point out that in this model, the channel is ideal. Both Eve and Bob see exactly what Alice transmits. So that's a key point here. And Shannon was able to show good news and bad news. The good news Shannon showed was that in a system like this, you can achieve perfect secrecy, where secrecy is in terms of information theoretic secrecy, meaning that Eve, the information that Eve can extract from X about M is 0. So that's the good news. The bad news is that in order for that to happen, you have to have a one-time pad. That is, key has to have at least as much entropy as the source. Or if these are if everything is binary, the key has to be as long as the source message. Okay. So that's good news and bad news. And in fact, for Shannon, what he was interested in back in the 40s was a cipher system that was used in World War II to communicate as a radio telephone system, communicating between Churchill and Roosevelt, between Washington and London. And the secret key was transferred on a record, in a briefcase, handcuffed to a courier's wrist. So there was a back channel to send the secret key, so you could have a one-time pad. Now, in a wireless system, of course, you have to use the wireless resources to transmit everything. So if you're going to transmit a secret key, you're going to need, it has to be transmitted in secret or it's not a key. And if it's as long as the message, you might as well just transmit the message in secret if you can do that. So this is not a practical issue. It's not a practical solution for a wireless network. Also, even in wireline networks, you rarely have one-time pad. Typically, you have a key which has much lower entropy than what you're going to transmit. You have like a crypto variable, which you blow up into a secret key that's much longer. But the actual number of bits of secrecy is usually much smaller than the messages. I think that's well known to people, how many bits of key you have, how many bits of crypto you have is much smaller than the actual key that you use. So it's very rare that you would actually use a result like this in practice. Now, move forward. So that was 1949. Let's move forward to 1975. So 25 years later, still a long time ago. Wyner, Aaron Wyner, both of these were at Bell Labs, by the way. Aaron Wyner modified Shannon's model. He took away the secret key and added the practical fact that you don't have a noiseless channel. You actually have a noisy channel between Alice and Bob and another noisy channel between Alice and Eve. And he was interested in the question as to whether you could somehow take advantage of the noisy channel to transmit secretly to Bob, transmit reliably to Bob, keeping it secret from Eve. And in fact, Wyner also had good news and bad news. So the way he formulated this problem, he wanted to trade off the reliable rate to Bob, which is the classical, thing you look at in data transmission, versus the equivocation at Eve. So the equivocation is just the, at Eve would here just be the entropy of the message conditioned on Eve's measurements. So if that were to equal the reliable rate to Bob, that means that you would be transmitting in perfect secrecy. So the secrecy capacity here is the maximum R, that is the maximum reliable rate to Bob, such that it's transmitted in perfect secrecy. And again, Wyner had good news and bad news. So Wyner's good news was the secrecy capacity can actually be positive. That is, you can transmit reliably and in perfect secrecy without a secret key. But it's true if and only if Eve has degraded measurements relative to Bob. So there's a specific definition of degradedness, but you might think about, say, Eve having a lower signal to noise ratio than Bob, say. Okay. So good news and bad news. It's possible, but you still have to have some advantage. But Bob has to have some advantage over Eve. Okay. So that's 1975. That's a long time ago. We can zoom forward 45 years, or maybe not quite 45 years, 35 years. And within the last decade, say, there's been a resurgence of interest in these ideas. And there are just two things to learn. One is, in general, in order to get secrecy, both Shannon and Wyner tell us that the legitimate receiver has to have some kind of advantage over the eavesdropper. Either you have to share a secret, like in Shannon's model, or you have to have a better channel, like in Wyner's model. So it seems like a pretty limited opportunity. But in fact, it's not, because the radio channel has certain physical properties, in particular diffusion and superposition, and I might add reciprocity to that provide opportunities for advantaging one receiver over an eavesdropper. So for example, fading, which is a natural thing in wireless channels, provides natural degradedness over time. So if you have two receivers that are fading independently, you're going to get, at times, you're going to have advantage one receiver over the other. Interference, which is superposition property, allows active countermeasures to eavesdropping, such as jamming. Okay, so that's another advantage in the physical layer that you can, another physical layer property you can take advantage of to get security or to advantage one receiver over another. Spatial diversity, multiple antenna systems, relays allow you to create secrecy degrees of freedom. So, again, you can take advantage of those degrees of freedom to transmit and securely advantaging one receiver over an eavesdropper. Also, random channels, since the wireless channel is random and there's reciprocity, the legitimate transmitter and legitimate receiver can share a source of common randomness between them, which the eavesdropper can't see. So you can use that to distill key. So basically, the first three of these phenomena lead to so-called secrecy capacity regions, that is, regions of rates where we can transmit in secret over the physical channel. And also it allows us to do, the fourth one allows us to distill common key on the fly, is something I mentioned a little bit earlier. So I'm just going to focus on this first phenomenon, that is the how you can take advantage of fading, but all of these are things that have been studied in some depth. So let me just mention briefly a couple of things, and then I'll go into a specific example. So, you know, of course, wireless networks are like organic molecules. They're sort of made up of all these smaller networks. So you can think about organic molecules as being made up of a lot of smaller organic molecules, the bonds. And wireless networks are like that. They're made up of a lot of smaller networks. So you have the broadcast channel, which is one transmitter, multiple receivers, multiple access. So that's like the downlink of a wireless network. You have multiple access channels, which is multiple transmitters, a single receiver. It's like the uplink of a wireless network. Interference channel, multiple transmitters, multiple receivers. That's like a multi-cell network, uplink or downlink. And then you have relay channels, MIMO channels, and so forth. And for all these channels, these basic channel models of wireless, physical layer security has been considered in the context of Wyner. That is, what is the secrecy, so-called secrecy capacity region for these fundamental primitives of networks? And there are papers on all of these things. A lot of work has been done, still going on. And I'll just point out a paper, it's a few years old now, in the Proceedings of the National Academy of Sciences, which reviews a lot of their progress up until that point. So let me just, as an example, look at the Gaussian broadcast channel. So here we have Alice, the legitimate receiver, and two receivers. We call them Bob 1 and Bob 2. And this is a so-called broadcast channel with confidential messages. So there are two messages, M1 and M2. So M1 is a message that is a broadcast message. Alice wants to share that with both receivers. And M2 is a message that's just to be shared only with Bob 1. So Bob 2, the lower receiver, is a legitimate receiver for message 1 and an eavesdropper for message 2. Or another way to think about this is for message 1, this is a broadcast channel, and for message 2, it's a wiretap channel. So, and this is a Gaussian broadcast channel, meaning that the two channels between Alice and Bob 1 and Alice and Bob 2 are additive white Gaussian noise channels. Okay. So what we can do is we can look at the so-called capacity region and secrecy capacity region, which are the rates of these two messages. So in this chart, this is for the case where the signal noise ratio at the top receiver is 10 dB and the signal noise ratio at the lower receiver is 5 dB. And on the horizontal axis, you see the range of rates for the common message. And on the vertical axis, you see the range of rates for the secret message. That is the message that's going only to the top receiver. And the red line, all the points below the red line is the actual capacity region of this broadcast channel. So it's the set of rates that you could send M1 and M2 to out through this channel reliably at without any secrecy constraints. And then the dashed blue line is the outer boundary of the so-called secrecy capacity region, which shows us the range of rates that we can get if we want to keep message M2 in secret from Bob 2. Okay, so you can see that we don't lose much in this particular example in the common rate, that is the horizontal range of rates, but we lose a lot in the rate of message 2, and that basically the gap between the red line and the dashed blue line that's some extra capacity that we have to use in order to confuse the eavesdropper about the message. So we do that by randomizing the message, and in doing that, we're using up capacity. Now it's interesting to look. So that basically tells us the picture for this particular snapshot of signal noise ratios. Now suppose we vary the signal noise ratio of the eavesdropper, keeping the signal noise ratio of the legitimate receiver at the top the same. Okay, so now I'm going to keep the top receiver has signal noise ratio 10 dB as before, and now I'm going to vary the signal noise ratio of the secondary receiver and from 2 dB to 6 dB, and as it decreases, you can see that we're going up in this to the right, upper right in this chart. So what happens is, and again, underneath any of these lines is the region that we're looking for. And what you can see here is that as we decrease the signal noise ratio of the eavesdropper, the range of common rates decreases, and that's because that's the bottleneck receiver. That is transmitting M1 reliably across this broadcast channel. The bottleneck is the weaker receiver. So as its SNR gets smaller, the range of possible rates decreases. On the other hand, the range of possible secrecy rates increases as we further degrade the secondary receiver. Now, what I haven't shown here is the case where the signal noise ratio of the secondary receiver equals that of the primary receiver. And I haven't shown it because that's the case that's the Wyner bad news case. There's no degradedness, and therefore the secrecy capacity collapses. So basically what would happen is that would just collapse to a line along the x-axis if we did that. So that's not a very interesting case, but it does show the limitations of this wiretap model in the Gaussian channel. Now, what about, though, I mentioned that we can use fading to overcome this need for this issue of needing to disadvantage one receiver, the eavesdropper. And so now let's look at the fading Gaussian broadcast channel. So in addition to having white Gaussian noise at both receivers, and now I'm just going to assume they have the same intensity of noise, let's assume that the channels between Alice and Bob 1 and Bob 2 are both Rayleigh fading. And so we'll assume that the fading coefficient, the fading intensity to Bob is a unitary efficiency, unitary value. So the gain, the random gain between Alice and Bob 1 has an exponential, one-sided exponential distribution with unit parameter, and between Alice and Bob 2, we have Rayleigh fading with parameter sigma 2. And if you remember your communications, when in Rayleigh fading, the smaller sigma 2 is, the more intense the fading is. Okay, so decreasing so we have the noise level is fixed, and we're just going to make the fading more intense, and that's a way of changing the channel to Bob 2. So we'll keep the fading the same to Bob 1. We're going to look at what happens when we vary the fading intensity of Bob 2. And you see we get a very, very similar picture to what we did when we changed the signal noise ratio of Bob 2. As the fading gets more intense on the secondary link, the range of common rates decreases and shrinks, but the range of secret rates increases. So exactly the same kind of thing as the secondary receiver gets worse. But one thing to note here is that's different from the additive white Gaussian noise channel is that we actually have the case in red where both channels are statistically identical. That is, neither channel is degraded with respect to the other. And you can see that even in that case, and in fact, it's true for any value of sigma 2. Sigma 2 could be even above 1, and we'd still have a non-trivial secrecy capacity region. So basically what we're seeing here is that the secrecy capacity region with fading never collapses. So that as long as we have fading, so it's very similar. Fading is our friend here, just like it is for, say, for MIMO channel or relay channel. We can take advantage of the fading to find opportunities to transmit in secrecy when the secondary receiver is in a deeper fade than the primary receiver. Okay, so that's an example to illustrate how the physical layer can be used to take advantage. We can take advantage of the physical layer in order to get reliable transmission to Bob while transmitting in perfect secrecy with regard to Eve. Okay, so now I want to talk a little bit about an issue I brought up at the beginning, which was the fact that the kind of results I'm showing here, I just showed you, these are asymptotic results. So all the Shannon and Wyner results are asymptotic results, asymptotic as the block length goes to infinity. Just that's the way traditional information theory is organized. So just say a little bit more about secrecy capacity. So here's another drawing of Wyner's wiretap channel with a little bit more detail. So remember, we have Alice with a message to be transmitted to Bob reliably and in secrecy relative to Eve over a channel. So the way that, to be a little more precise about that, the way we do that is first of all, the message is mapped to a sequence of n channel uses. So X is a typical input to the channel. Xn is a sequence of length n of those inputs. And then the channel has two outputs. One is Bob's observation and one is Eve's observations. And there are also, each of those is also a sequence of n things. So X1 goes into the channel and Y1 and Z1 come out, X2 and so forth and so on. So then Bob and Eve each have a sequence, n-long sequence of measurements, and they'd like to reconstruct Alice's message W. So Bob gets an estimate of W. Eve would like to estimate W, but we're going to put an upper bound on the information leakage between W and whatever the best that Eve can do. We'll call that delta. And then the secrecy capacity region is going to be, in this classical sense, is an asymptotic region. So you let the block length n, that is the number of channel uses, go to infinity. The probability of error at Bob go to 0. That is the probability that W hat doesn't equal W. And the information leakage go to 0 as well. So you're getting perfect secrecy in this and perfect reliability in this limit as n goes to infinity. And what Wyner showed, this is a little bit of an oversimplification, but it's a good way to think about it intuitively. What Wyner showed was that in this model, the secrecy capacity is the maximum over all channel input distributions of the difference between the mutual information between the input and the output of the channel on a single channel use, between the mutual information between the input of the channel and Bob's output minus the mutual information between the input of the channel and Eve's output. So that's the secrecy capacity in this model. Is a slight oversimplification, but it holds in most cases, and particularly holds in the Gaussian and Rayleigh cases that I showed you. So this is the very nicely intuitive result. It shows very clearly what you mean by degradedness. It's a clean result that gives rise to the kind of results I just showed you. On the other hand, it is asymptotic. So we're not, for short packets, like we might have in IoT, we're not going to have n go to infinity. We're not likely going to have the probability of error go to 0. And we probably can't expect the information leakage to go to 0 either. So all of these things are going to be finite, that is non-asymptotic. So for something like IoT, this is not a very useful, or at least it's not the most useful formulation. So what can we do? Well, over the last 10 years or so, there's also been a lot of interest in trying to create non-asymptotic information theory. And here's an early result in this area. This is Yuri Polyansky, a former Princeton student who's now at MIT. This was in his PhD thesis. And here you have a source, again, W, we can take one of m values. So the number of bits per symbol is log 2m per source symbol. It's going into an encoder, which is going to create n channel symbols. those are going to go into the channel. We get we get in channel outputs, which are going to go into a decoder, and which tries to reconstruct the original transmitted source. So for such a channel, we're interested in n, m, epsilon codes, which is a code that for a given block length n, that is a given number of channel uses n, and a given source dimension m, and a given, it can achieve error probability, symbol error probability of no more than epsilon. So a code, any encoder decoder pair that can achieve that is an n-m epsilon code. And then a fundamental limit for any channel is the maximum size source, that is the largest number of bits you can transmit through the channel, such that there's an n-m epsilon code. So this is a function of the block length and the error probability epsilon. Now, if we take the log of this and divide by n and let n go to infinity and epsilon go to 0, we get the Shannon capacity. That's one of Shannon's fundamental results. That's the capacity of a channel. It's asymptotic. So what about if we don't have an asymptotic situation? What if n and epsilon are finite? Well, it turns out we can get a pretty good approximation to the log of m star, which looks like which has only two terms, so plus higher order terms. So the first term, of course, is n times Shannon capacity, because we know if we divide by n and let n go to infinity, we get Shannon's capacity c. The next term is root n, it's negative root n times another term v, it's called a dispersion, times q inverse of epsilon, where q is just the tail of the unit Gaussian distribution, and q inverse is its inverse function. So you see, now we have an expression that depends on n and epsilon, and it has Shannon's capacity, which is well known, plus this new term, the dispersion. So what is the dispersion? Well, the Shannon's capacity, you might remember, remember Shannon's capacity is achieved by looking at the maximum of the mutual information between the channel input and channel output, maximized over the input distribution of x, the distribution of x. So if you choose x to be a random variable that has that input distribution, the one that maximizes, call it x star, then y star is a channel output variable, then let I be the so-called information density, then the expected value of that information density evaluated at x star y star is the capacity. That's how you get the capacity. Now, the variance of that same random variable whose mean is the capacity is the dispersion. So you see, we're getting here a very nice result where the first term, the leading term, is Shannon's capacity. The second order term, or the first higher order term, is based on the variance of the random variable whose mean is Shannon's capacity. And then there are some higher order terms. But it turns out that if we just look at we can use that as an approximation and get quite a good approximation to capacity for finite block length. And here's an example. This is the additive white Gaussian noise channel. The signal noise ratio is 0 dB. Epsilon is 10 to the minus third. And for those parameters in additive white Gaussian noise, the Shannon capacity is 1/2. And what we've shown here is a plot versus block length of the log of the actual m star divided by n as a function of n, the block length, for that particular epsilon. And the red line is a converse bound, it's the upper bound, and the blue line is the so-called achievability bound. It's a lower bound on that finite block length capacity. And you can see that there's not much room between the upper and lower bounds. So we know that between those two bounds is the actual capacity. And we can see that for short packets, typical IoT packets are 100 or 200 bits. You can see that there's quite a gap between whatever the actual capacity is, it's between those two lines. And there's a substantial gap, maybe a factor of 2, between that and the actual capacity. Okay, so this is for channel capacity. This has nothing to do with the wiretap channel, but we can do a similar thing for the wiretap channel. And so here's a short analysis of that. This is work with Wei Yang and Raphael Schaefer. It appeared in the information theory transactions. So here we have again Wyner's wiretap channel, and just like we talked about an NM epsilon code for a traditional channel, here we can talk about an NM epsilon delta secrecy code. So we have finite block length N, message size M, fidelity at Bob epsilon, and leakage at Eve delta. And we'd like to find the rate, that is the maximum M, for fixed N, epsilon, and delta for a given block length, epsilon and delta. Okay, so that's like a finite block length version or a non-asymptotic version of the secrecy capacity. And now we don't have a general result like the one that you saw for from Polyansky and others, but we can show for particular wiretap channels, we can show, we can get upper and lower bounds, just like we do for that general case. I'm trying to get this out of the, if I can get this out of the way. Okay, I can't do it. Yeah, here we go. Maybe I got it. There we go. Okay, so, oops. So this is for the semi-deterministic wiretap channel, which means that the direct channel is deterministic and the eavesdropper's channel is a binary symmetric channel. And you can see we have a very similar expression for the finite block length secrecy rate, maximum secrecy rate. It's the secrecy capacity, which we've already looked at, corrected by a term, a 1 over root n term, and another quantity v, which is a variance similar relative to the secrecy capacity, similar to the dispersion relative to the Shannon capacity. And for this particular example, again, we've chosen an example where the secrecy capacity is a half. And again, you can see we have not quite as tight of upper and lower bounds, but you can see that we do have converse and achievability bounds that fairly tightly bound upper and lower the actual non-asymptotic secrecy capacity. And again, there's quite a gap to the Wyner type secrecy capacity here. And we can do something similar for the Gaussian wiretap channel. Here the bounds are looser, but also they point to a big gap between the secrecy capacity and the actual finite block length secrecy capacity and so forth. So that allows us then to start looking at finite block length issues for like in IoT, looking at secrecy capacity for those kinds of URLLC communication situations. Okay, so I'm going to shift gears now. I got about 10 minutes, so I'm going to try to do this fairly quickly. I'm not going to talk about data transmission anymore. I'm going to talk now about privacy instead of security. And just to draw a distinction, and I'm going to focus on sensing systems. So again, this is really focused on something like IoT rather than data transmission. And I'll just want to point out that privacy and secrecy are not the same thing. So secrecy is this model that I show here. You've got a legitimate receiver, Bob, and an eavesdropper, Eve, and you're trying to keep the message going to Bob is you want it to be there reliably and completely, but in secret from Eve. Now, privacy is a little different. You don't necessarily have an eavesdropper, but you still have a recipient of the message, and you might like to have some idea, you might like to maintain some privacy of some elements of the information that Alice has available to her while transmitting some elements of it that she doesn't mind disclosing to Bob. So you can think about, in privacy, you can think about there not being an eavesdropper. There's a legitimate receiver for some parts of the message, but also with regard to other parts of the message, that receiver is in fact an eavesdropper. Okay, so it's a little different kind of thing. So denial of service is not what we want to do here. We'd rather try to achieve some kind of trade-off between revealing information and keeping other information private. So, think about, various kinds of IoT devices, cameras, motion sensors, smart meters, and so forth. I mean, they all generate data. And again, the utility of that data depends on its accessibility. So the whole idea of having sensors is you collect data and you share it with at some common point. But on the other hand, if you make it all accessible, that endangers privacy. So there's a trade-off, fundamental trade-off between, on the one hand, keeping data private and secret, and on the other hand, making it completely accessible. There's sort of two contrasting goals. So that trade-off is something we can examine using information theory. So in particular, we can look at utility privacy trade-off regions. That is, for example, if we let distortion be a measure of utility, so it's an inverse measure of utility, and let equivocation be a measure of privacy, then the higher the equivocation, the more privacy, and the lower the distortion, the more utility. Then we can generate a so-called utility privacy trade-off region. It's a little bit like a rate distortion region. And in fact, that's one way of getting at it, is to take rate distortion analysis with an equivocation constraint. And the outer boundary of that region is like something like an efficient frontier. That is, this kind of region doesn't tell us where to operate. It just tells us how much privacy we have to give up for a given level of utility, or in contrast, how much utility we can get with a given privacy constraint. And that's just a point along that outer curve. So we can apply this kind of analysis to various specific situations. For example, we can look at smart meters. A smart meter is, of course, an electricity meter that reports usage in almost real time. And of course, it does that because it makes the power grid more efficient, right? You can do load balancing, price aware usage, and so forth, but it leaks information. It's well known that smart meter traces leak information. Now, it turns out that we can apply a fairly good model to this, where we can look at privacy utility trade-off, where we measure privacy in terms of leakage about transient events, which are the most informative ones, and utility in terms of how much the mean squared error between the reported usage and the actual usage. And when we do that, if we model the intermittent state as a hidden Gauss-Markov model, it turns out we can get the optimal trade-off by using so-called reverse water filling. That is, if you look at the spectrum of the utility, the smart meter trace, and we set a water level, and we suppress those elements of the spectrum that are less than the water level, and we allow the others to go through undistorted, that gives us the optimal trade-off between utility and privacy in this case. And if you want to move the water level up and down, you trace out the efficient frontier. So a lower fee gives you greater utility and less privacy, and a higher fee gives you the opposite. So it's a very clean solution that gives us utility privacy trade-off in that problem. Now, I'm going to go very briefly over the rest because I'm running low on time, but we can also, if we have a battery, we can also use the battery, control of the battery, to trade off utility and privacy. And in this case, in order to get privacy, we have to waste some energy. So here we trade off wasted energy versus information leakage. So that's the privacy utility trade-off. And we can set this up as a Markov decision problem. And it turns out that we can get numerically, for certain examples, we can get a lower frontier that tells us how we can optimally control the battery in order to trade off those two elements. Sorry to go fast over that, but I'm running low on time. I also want to mention something called competitive privacy, where we have multiple interacting agents that are trying to, each has its own sensing task, and they have correlated measurements. So they could help each other by sharing measurements, but in doing that, they reveal private information. So this is so-called competitive privacy. And you might ask the question, how should they interact? So this could come up, for example, in the electric grid, where you have different utilities who are trying to manage the grid together. They could share measurements, but then they're giving away perhaps some private trade data. You could think about radars for two different allies who have a common enemy, but they don't really trust each other. They could do a better job of tracking the enemy aircraft, if you will, if they share radar data. But on the other hand, they may not want to share too much data because they don't trust each other. Or you could be looking for oil out in the Gulf of Mexico, and you have two different oil companies, and they're both doing seismographic measurements, and they could share data, and they could better explore oil for oil. But then, of course, they would be giving away some of their own information. So you can see various sensing applications where you can have this kind of trade-off. So basically, we could set this up as a linear measurement model where we try to trade off mean squared error and state estimation versus leakage of information about a given state to other agents. And it turns out that this is also an information theoretically solvable problem. In particular, we can see that this is a distributed source coding problem. So Wyner Ziv coding tells us exactly how we should share information, but it doesn't tell us how much information we can share. And that instead can come from looking at game theory. So there's a lot of game theoretic aspects here where you can see let's look at the effects of pricing, cooperation, multiplayer games, and so forth, which I won't go into. I'll just point to this book chapter here, and I'm going to share these slides later so you can go back and look at these. But basically, this is just to point out that there's also this issue of competitiveness that can come into these privacy utility trade-off problems. Okay, well, I just very briefly mentioned a couple of other issues. I won't go into any of these in depth, but we can look at other security primitives. I've talked about this privacy utility trade-off, and I talked about data transmission, but there's also all kinds of other things that we can look at: authentication, malicious nodes, issues of malicious nodes, either trying to eavesdrop in an ad hoc network, or to induce some kind of spoofing or man-in-the-middle type attacks. And these are things that have been looked at using information theoretic methods. And again, since I'm about out of time, I don't think I'll go into any of these in depth. I'll share the slides and you can look at some of these things later if you're interested. So let me just wrap up then, and then I'll take questions. First of all, basic message here is that we can use information theoretic ideas to help understand some fundamental limits on security and privacy in wireless networks. And I've really focused on sensing, Internet of Things kind of networks, which is where I think the need is here. Everything I've talked about here is really theoretical, although some of them do point to practical solutions, like particularly in smart metering. I think you can see pretty easily how to put that into a practical solution. But there are a lot of other issues that need to be considered. I mean, for example, finite block length analysis, certainly a lot more needs to be done there. I mean, we have just the wiretap channel, but there are many, many other channels out there to look at. Scaling laws for large networks. I mean, most of everything I've talked about here has involved very small numbers of terminals. And of course, one of the principal features of IoT is massive deployment. So that's certainly something that needs to be looked at. Practical coding schemes. So when you have a capacity region, the next thing you ask is, well, how can I achieve that capacity in practice? And so we need to look at practical coding schemes, although there is quite a bit of work using LDPC codes and things of that sort, polar codes, to achieve some of these limits. And then other security primitives. I mentioned very briefly at the end authentication, but there's also all kinds of other things that need to be considered in security, of course. So just one final thought here. One thing about physical layer security is it's not ironclad. So it's kind of in some ways, a best effort kind of security. It can be good, but it may not be perfect. And so if you need to do your banking, or perhaps if you're a general trying to manage a battle, you may not want to use physical layer security because it's the best effort. On the other hand, for many applications like content distribution, for example, there's a trade-off between the cost of security and the amount of security you get. So we can think about, just like we talk about quality of service in wireless networks, we also should be thinking about quality of security. So do we really need bulletproof security for content distribution, for example? In other words, if I'm Comcast and I have some customers who get all my content and other customers who just get some premium content, well, that's a financial issue, right? It's not a life or death issue. And so if I'm willing to spend less on security just to prevent a few people from stealing some of my content, maybe that's a worthwhile trade-off. So we have to think about quality of security as being a parameter of networks. And when we do that, physical layer security certainly has a role in providing certain levels of security in certain situations. So that's really, I think, a good way to think about this as a closing comment. So with that, I'll just flash these references up again, and then I'll say thank you, and I'm happy to take questions. I see there's some questions in the chat.
So let us first thank Professor Vincent for an excellent talk.
Thank you.
So we do have a few questions, and I'll call up their names in that sequence so that they get the priority. So Ardhendu, you can ask your question.
Okay.
Hello.
Hi.
Hi, Professor Booth. Thank you for the very nice talk. It was a very nice overview, and you brought in together several decades of, I guess, a decade of work. Yeah. My basic question, actually, I got it right at the beginning. And there's a lot of talk about privacy, and there's a lot of new work on differential privacy, for instance. And the main sort of pushing factor there is that what if there is side information available to Eve, right? So when you talked about the Wyner channel, you had the Z, which was received by Eve on the channel itself.
Yes.
And then the Wyner optimization was something like, if you want to make sure that the entropy of the message given Z is not too high, or is too high, right?
Yes.
And so, but then what if, so that's the standard question that always comes up. Like, what if Eve has some side information? That is like adding an extra random variable to that conditioning there, right? And
yes.
So I think Shannon's, given that the key is properly generated, Shannon's ciphertext doesn't have that problem, but Wyner guarantee would be reduced or
yeah, absolutely. It definitely changes the degradedness, right? I mean, if that side information is correlated with the message, it's going to change the degradedness. So yeah, absolutely, that would matter. I mean, there, by the way, you may know there is a lot of work on wiretap channels with side information, both at Bob and at Eve. So there is work in that area, but you're right. I mean, your intuition is completely correct. I mean, the formulation, basically the formulation works just looking at, you don't necessarily have to look at that construct that I gave you where Z is coming out of the channel. You can think about Z as being constructed both of something coming out of the channel and some side information. So yeah, so your intuition is completely correct. That's true. Yeah, thank you. Good question.
Thank you. And just one more question, which I got up towards the end. So you have this nice finite block length, converse, and achievability. So, and you mentioned a bit about LDPC codes and how they could be actually achieved. My basic question is, I do not know a lot about the achievability schemes, but even in standard coding, of codes to approach the channel capacity, right? On standard additive white Gaussian noise channels, for instance.
Yeah, I'm sorry, you cut out
the achievability.
a second. Could you just backtrack about maybe 30 seconds? Because you cut out just a little bit, yeah.
Sorry, yeah. My short question is basically the achievability schemes for your secrecy constraint capacity region in the, say, the finite block length, or are they different from the achievability schemes in standard additive white Gaussian noise channels?
Well, they are. I mean, there are some. They're LDPC because they're different codes, of course. And one thing you notice in those charts that forget about the secrecy part. You have to have a pretty long block length to get close to channel capacity. So even an optimal code has to have a pretty long block length to get close to Shannon capacity anyway. I mean, the asymptotics and the additive white Gaussian noise channel kick in pretty late. So I mean, it's a long tail there. But yeah, but it's similar. Yeah, it's very similar type.
Okay. Thank you.
Mm-hmm. Yeah, thanks for your questions.
Shamik, you are next.
Hello.
Yes.
Hello, Professor Poor.
Thank
you for your talk. I had some question. I do not really work on wireless, but I was wondering what I got from your talk is that the defender is trying to make sure that it could utilize some of the physical properties of the channel to improve the secrecy, right? So if I am thinking of an active adversary, can the adversary also try to do something in the wireless medium in order to prevent the defender from utilizing the physical property properly? Like, for example, he's also trying to make sure that the defender is not able to utilize the variation in the fading intensity. So is there some research or assumptions in that side?
That's a good question, Shamik. Yeah, so yeah, I mean, everything I talked about here is a passive eavesdropper. But yeah, there is work on, on active eavesdropping. I mean, the worst, active countermeasures, the main thing is denial of service, right? I mean, that's kind of like jamming, right? I mean, that's almost like an obvious thing. Sure. I mean, the whole game is trying to somehow disadvantage the game for the legitimate receiver is to disadvantage the eavesdropper, and the game for the eavesdropper is to disadvantage the legitimate receiver. So yeah, I mean, if it's an active eavesdropper, there are things that can certainly be done. And in IoT, of course, you could do spoofing or, man in the middle, all those kind of things could come up. I mean, they're not exactly in the context that I've talked here, but there is work of an information theoretic nature on those kind of problems too. But yeah, that's a whole nother area. And yes, there is research in that area.
Sure. My second question is that, do you think that the advances in machine learning can help give us or the adversary some benefit in terms of learning some of the physical properties in the medium, which because some of the machine learning techniques also use information theory. So do you think that there is a common link between what people work in wireless and what people who work in statistical learning theory?
Well, I mean, not specifically about things like security, but I mean, yeah, there's a lot of interest in machine learning and wireless networks. And particularly, in fact, I have a book with some colleagues coming out, machine learning and wireless networks. So it's a big area, and it's an obvious area because wireless networks have a lot of they're basically they're making inferences, they're controlling things. So all those things that machine learning are good at are things that you want to do in wireless networks. And there's a lot of data because you transmit it, gigabit rate. So you've got a new exemplar, a billion of them a second. So, yeah. And in traditional wireless networks, let's say more you know, like cellular networks, for example, of an earlier era, even up to 5G, I would guess, 4G certainly. You know, the model-based, the whole the ethos has been model-based design, right? Not data-driven design. But with a lot of these modern networks, you know, with IoT and there's a lot of interference, and everything is very the models start breaking down basically when you have massive numbers of devices. And so machine learning is definitely one of the things that people are looking at to try to get a handle on how to optimize these networks. And even if you know a model, there is some work, and you're probably familiar with this, that shows that you can do model-based machine learning and often get lower complexity type solutions, right? So even if you have a good model, you might want to use machine learning just to get lower complexity. You know, a neural network might be of lower complexity than some channel decoder that you could build. And it also gives you the opportunity to use more complicated codes that you might not have a good decoder for. So yeah, I mean, definitely, just in general in wireless networks, machine learning is very important, or more of emerging importance, I should say. Now, for secrecy, you know, yes, I'm sure. You know, I mean, for example, in code design, you might want to use machine learning, right? You could do auto encoding, for example, and I think that could be a big help. You know, these fundamentals, you know, it doesn't matter. They're really completely agnostic as to the processing that you do, right? So in some ways, the things I talked about today, at least the theoretical work, doesn't really, you know, machine learning is kind of irrelevant there, just because it's kind of a solution suite, right? But if you actually want to build a practical system, that's when machine learning, I think, could have a big role, because not as much is known about how to design codes and so forth for these kind of applications as there is for more traditional communication systems. So yeah, I think machine learning could be a good path for trying to find some ways of bringing these ideas into practice.
Okay, yeah, thank you.
Good question.
Before I go to the next question, I had one question. I could see that you have a reference from SPOC 2020, your paper.
Yeah.
So the question is basically, if you could highlight a little bit, because we are looking into federated learning for privacy preservation in general, in IoT devices and application smart grid. And I see that you have a paper there. If you could just give a little highlighting of that, what this paper is about, and how do you apply federated learning for privacy preservation?
Yeah, so that's good. In fact, if I hadn't run out of time, I was going to talk a little bit about that. So you gave me an opportunity to do that. Yeah, so I mean, of course, you know, federated learning originally sort of privacy preserving, right, was the kind of mantra. But then people quickly learned that, you know, you could infer the data from the gradients or from the parameters, right? So there's a lot, as you know, there's a lot of work on trying to put privacy into federated learning. And what we did in that paper was we just tried to get some bounds based on information theory on how much privacy could leak. So looking, say, at the mutual information between the gradient and the data, you can, you know, you're starting to look at how much privacy can be leaked. So that's what that paper's about. And we also looked at generalization error too, but that was, in terms of privacy leakage, is you know, it's kind of a you know, it's not straightforward analytically, but it's kind of straightforward conceptually. You want to know, is there information in the gradient, or is there information in the you know, the derived parameters for the neural network about the original data? And obviously there is, right? Because they're functions of the data, right? So there is information in there. The question we tried to address here in this paper was how much. And we have some bounds. We don't have exact results, but we have bounds. But that's what that's about. Yeah, I'm glad you mentioned that, because I had wanted to mention that. So in general, you know, as was mentioned earlier, there is work on looking at information theoretic properties of neural networks and other machine learning algorithms. And that's kind of what we're trying to get at there. So.
In particular, what we are looking at, for example, federated learning, by definition, you share information without revealing secrets, right, or revealing the privacy. But when you have edge analytics and you have the cloud, the question is what are the parts that you send to the cloud, and there's a privacy breach possibilities there, and then what model do you share back to the edge, right?
Right. Yeah. So all those problems, I think, have information theoretic formulations that can help you understand the leakage. I think when you get to how do you prevent the leakage, then things like differential privacy and other things. Yeah, or there is this analog federated learning where all the combining is done in the air, right? So you never decode the gradient; it's just all added at the receiver. Of course, eavesdropper could pick that up too, but I mean, at least the aggregation point can't make inferences about the data. So yeah, I think that's a really fascinating area and very rich. And I think we're learning a lot more about federated learning as we go along, because like I said, originally everybody said, oh, this is privacy preserving because we don't share the data, so it's not true.
Do you have time for one more question? Seed actually has another.
Fine, I'm just in my kitchen.
Sure.
I'm on sabbatical, Shajal.
Okay, that's very good. Then thank you. Because usually, since you are not getting the opportunity to meet the speaker, so people stick around and then ask questions more like this kind of discussions, which is very rich. So Seed, you are next.
So, hello, Professor Poor. It's good to see you after a very long time again.
Yeah, nice to see you too.
To see you. So the question that I had was, I mean, you were talking about a certain compromise that we make in terms of channel capacity in order to obtain secrecy capacity. I was wondering, is there a way that we can detect the presence of Eve, maybe through some sort of channel distortions that it creates? If so, then we can potentially use it to our advantage. That's the...
Let me make a comment first, and then I'll get that question. So, in fact, with multiple antennas, you can, I didn't show that example, but with multiple antennas, you can get secrecy capacity equal to the channel capacity. So there actually are ways that you can not lose that rate by taking advantage of other degrees of freedom besides the temporal degrees of freedom you take advantage of with wiretap code. But put that aside, the best example I know of what you're suggesting, Sid, is in a quantum situation where you're transmitting down a fiber. Then you can detect if a photon is absorbed in the fiber, then there was a wiretapper in there, right? And then you can retransmit or something, do something different. So definitely in a sort of quantum communication setting, you can detect the presence of an eavesdropper, right? Because as soon as somebody measures the field, it changes the field, and that can be detected. In a radio frequency, maybe. I mean, if you think about the eavesdropper as being, which you would normally, as being a physical transmitter out there or physical receiver out there, it does change the field, and perhaps you could, by some method, I don't know, haven't seen anything like that. Perhaps you could do something that's similar, but I don't know about that. But maybe you could.
I was just wondering, because maybe not in the primary spectrum that's being under focus, but what about the harmonics and so on and so forth?
Oh yeah, the intermediate frequency or whatever in the receiver. Yeah, that's interesting. Yeah, I mean, certainly you can't really hide if you have a radio receiver completely, because you have to radiate. Even a receiver radiates something, right? So yeah, I hadn't thought about that at all. Yeah, that's interesting. Yeah. So from a practical point of view, you know, if you look in on the movies, they always have these machines they can go around and look for bugs, right? And how do they do that? Well, they're radiating energy.
Right.
So but I guess you could think about doing that more broadly. Yeah.
Okay.
That's a good question, Sid. I hadn't thought about that. So.
Wonderful. I don't see any more questions on the chat, but still, I think the speaker is happy to answer any questions that you may have. Anything else that you may have, even if it is your second question, third question, that's perfectly all right.
So maybe I can ask you a question about.
I knew, Sid. I think you have. I think Vincent is in your academic genealogy somewhere. You mentioned, right?
Yes. So my advisor, Professor Vashne, was Professor Haddad's student, Abraham Haddad, who was your advisor's.
Haddad and I, Abe Haddad and I are academic brothers.
Right.
Right. So you're my academic second cousin or something, or nephew, no, grandnephew. You're something like my academic grandnephew or something like that. So I don't quite understand how it goes, but yeah, we're in the same tree.
Right. In fact, if I go back, my PhD dissertation actually tries to bring in some of the elements of your work in physical layer security and distributed detection. So it's quite interesting that you have influenced quite a bit about my research.
Good.
So talking about the second question, I was very curious about your competitive privacy setting. Can you elaborate a little more about that?
Yeah, so I went very quickly over that, and I'm sorry, I just didn't have much time. Let me go back there and see if I can say a little bit more. So the idea here is, you know, you have I started out talking about privacy utility trade-off for a single agent, right? Now, suppose you have two agents, and they're each trying to estimate some parameters that are of interest to them, but they have coupled measurements with the two agents have coupled measurements. So think about the example I gave that I like to use is the electricity grid. So I'll go here. So look at this up on the right. So the way the electricity grid is managed is there's these RTOs, which every day they decide how much they predict the load, and they decide how much generation to put online. But the grid, they're regional. So the one I'm in, so you're in that big green one out in the Midwest. I'm in this blue one in the East. But the grid is not independent. I mean, you can see that the PJM where I am goes all the way out to Chicago, and in fact skips over some space. So it's the same grid. It's just they're managing different parts of it. So there's an advantage to sharing measurements, right? Because they want to estimate this. They only care about the state of their part of the grid, but it's related to the state of the other parts of the grid. So they could share measurements with one another, and that's fine. But the measurements may be coming from private utilities, right, who are competitors. Mm-hmm. So, you know, on the one hand, if they share measurements, they get a better state estimate, and they make a better, they make better decisions. On the other hand, they may give away some important proprietary information by doing that. So each one of them has a trade-off between privacy and utility, but it's different because it's not. They're not getting much. You know, they're going to give away privacy, and if they don't get any, if they tell the one agent tells the other agent their measurements, and the other agent doesn't reciprocate, then they've just given away privacy without getting any utility. Right. So that's why it's a game theoretic problem, because, you know, it's a competitive game, and so they're trying to play the game of trying to decide how much information to give in this competitive environment. And what I was talking about, the Wyner Ziv problem is, you know, it's really a distributed source coding problem. You know, it's the information leakage is like mutual information, right? So it's really just if you're going to exchange information where somehow you've got a constraint on mutual information, Wyner Ziv is the right way to do it. So if you're going to exchange information, once you've decided how much you're going to exchange, you should use Wyner Ziv coding. That's the most efficient way to do it. But the real question is not how to exchange information, it's how much information to exchange because of this competitive problem issue. So that's where game theory comes into play, and you've given me an opportunity to talk a little bit more about this. So, you know, it's basically a prisoner's dilemma in its basic form. That is, the best strategy is not to share any information because there's no guarantee you're going to get information back. So it points to the need to have some kind of regulation or pricing or something else that induces people to share information. And in the real electricity market, we have regulation that does that. But without that, you know, we might have a much less effective, you know, process going on. And that's sort of what the game theory shows. So that's a little bit more elaboration on that problem.
So were you able to get results that are better than not sharing at all in your analysis? Because
yes,
prisoner's dilemma, the equilibrium is to defect. That's as good as not cooperating. I was wondering, is cooperation playing a role in the equilibrium here?
So the way, the kind of results you can get, and I don't have any slides on it here, I'm sorry, but the kind of results you can get are if you reward people for information, of course you get a different, you know, equilibrium point, right?
Right.
So, but that, whether that's better or worse, it just depends on whether you agree with pricing, right?
Right.
And then cooperation means you set up a game with a common utility function. So it's not like you have two different decision makers, but you have a common utility function. So cooperation then gives you a higher utility than not cooperating. But again, you have to agree that the common utility function is better than the two independent utility functions. And then the third one, though, is I think more interesting, which is multiplayer games. So if you're going to play the game a finite number of times, it's a prisoner's dilemma. But if you're going to play the game an infinite number of times, depending on certain parameters, it may not be a prisoner's dilemma anymore.
Right.
So if you know you're going to play the game forever, you'll behave differently than if you know you're going to play the game for a finite number of times. And so that's to me the most interesting case. The other two are kind of obvious. You know, you just incentivize cooperation and they cooperate. But the other one is kind of more, to me, a little more interesting. And it's not just in this problem. I mean, there are other, it's known in game theory that infinite play games have different solutions than a finite numbers of plays. So, and that comes up here. So there's a paper, if you're interested, send me an email. I'll send you the paper that looks at this. Mm-hmm.
Vincent, you can send me the slides at your convenience, then I'll share with whoever wants.
Okay, will do.
And so how did you use the prospect theory in this context? In terms of human behavior, yeah. In terms of human behavioral modeling, especially we look into some of the prospect theory in the smart energy consumption on the user side.
Yeah, so prospect theory, if the decision makers are humans, then there's this irrationality that comes into play. And so the utility functions are modified to take that into account. You can be risk averse, okay, or you know, that kind of thing.
Your game theory includes that prospect theoretic aspects.
Yeah. So it's kind of like game theory, but you don't use the utility directly. You have the risk. You add the risk aversion.
Averseness, yeah.
Yeah. So yeah,
risk awareness. Yeah.
That's not in that paper, but I have another paper on that if you're interested too. So yeah. So prospect theory. You know, if you think about, then you might think about, like, for example, demand side management, right, an electricity grid, where it's a homeowner who's trying to decide where to operate, right? And then you have to put prospect theory, because in fact it's known the utilities have tried various strategies that don't really work in time to getting consumers to do certain things, right? To use less energy.
Yeah, one could be risk, another could be their malicious or selfish intent, right?
Yeah. Well, there's that, but I mean, consumers aren't good at estimating,
optimizing.
Risk, and they tend to over and under estimate probabilities and so forth near the edges. So we're humans, all humans do, not just, I shouldn't just say consumers, we all do that. So that's where prospect theory comes in. It's just really modifying the game theory to take advantage of risk. And
you mentioned that's a different paper?
Yeah, that's a different paper, but I can send you that.
I'll appreciate it. Yeah.
Okay.
Wonderful.
Okay.
Any other questions, comments? Otherwise, I think it's about 11:30 now, and Professor Pouris has been talking for the last 1.5 hours. So thank you so much again, Vincent. I really appreciate it, and you can see that the interest that has been generated, and people are still sticking around to listen and ask questions.
All right, well, good. It was a pleasure. Thank you, Sajal, for the invitation, and I hope to get out to Rolla sometime
I think we'll look forward to that. Definitely.
Okay, great. Take care.
Okay, you have a nice day.